Greetings and welcome to a series of lectures on exponential and logarithmic functions. In this lecture, we'll discuss what a common logarithm is and natural logarithms. Right, common logarithms and natural logarithms. Let's talk about this a little bit. Common logarithm is the logarithm with a base 10. So instead of saying log base 10x, we're just going to say log x. The base is assumed to be 10. Common logarithms, well, if log base 10 equals 1, remember our rule, then log 10 will equal 1. Log of 1,000, we can rewrite 1,000 as log 10 cubed. Bring our rule of our exponent, we're going to bring it out front, so it's 3 times log 10. Well, since log 10 is 1, right up there, 3 times 1 is 3. Okay. We're going to do this quite a bit right now, so let's keep going. Log 100, well, that's the same thing as log 10 squared. We can bring the 2 out front, so it's 2 times log 10. Log 10 is 1, so 2 times 1 is 2. Log 10, well, log 10 to the first power, bring the 1 down front. 1 times log 10 is 1. Log 10 is 1, so 1 times 1 is 1. Log 1. Well, log 1 we can rewrite as log 10 to the first, or pardon me, log 10 to the 0 power. Bring the 0 down front. 0 times anything is 0. Log 0.1, I can write that 0.1 is 10 to the negative 1. Bring the negative 1 down front. So negative 1 times 1 is negative 1. See kind of where this is going? If anything, these aren't too bad, right? These are kind of fun to do. Once you get the hang of it, no problem. All right. Log 0.01, I can write that as log 10 to the negative 2. Therefore, my answer is going to be negative 2. Bring the negative 2 out front. Log 10 is 1, therefore it's negative 2. Log 0.001, well, that's log of 10 to the negative 3. The proper procedure is to bring the negative 3 out front, and log 10 is a 1, so negative 3 times 1 is negative 3. Right, most of us have smartphones, and on our smartphones there's a scientific calculator. There's a calculator if you turn it one way. So if I turn it this way, it's just a regular old calculator. But if I put it into landscape mode, you'll see that it switches to a scientific calculator. Scientific calculators has a log button. Right there is on mine. So how you calculate it with base 10 is going to be this log button. So let's figure out the log of 7.2. So 7.02 log, oops. I always forget my calculator's the opposite way. Log 7.02, you can see it's approximately 0.8463. We can do another one. Clear. Log of 1.39 is approximately 0.430. If I did another one, clear. Log of 6.77815, so we're going to round that to 0.7782. And log of 9.99. Clear. Log 9.99. Right? It's 0.9995. Because I'm taking the log of a number smaller than 10, my answer better be a decimal, right? Because it's smaller than 10. We have to raise 10 to a smaller power than 1 to be able to come up with a smaller number. If this number that I was taking was larger than 10, then I'm going to have a number larger than 1. All right, so we're going to use a calculator to find the log of 2,760. So log 2,760 is going to be 3.4409, blah, 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 blah. Okay. Here's the thing. The 3 is called the characteristic. The decimal portion is called the mantissa. They're names that we give these things. 3 is the characteristic, and the decimal is the mantissa. Let's use our calculator to find the log of 0.0391. Log of 0.0391. In this case, our characteristic is -1. Because it's a decimal, remember the decimal, the power is a -1 because I'm a decimal. So the characteristic is a negative number. Therefore, we're taking the log of a decimal. And then the mantissa is 0.4078, we'll call it. Characteristic will tell us if it is a number greater than, number greater than 1. And the mantissa will tell us what portion of the power we need extra. Kind of, sort of. The characteristic, I think, is more important to me than the mantissa. The characteristic will tell me if I'm a fraction or not. If I am a negative number, I've got to be a fraction. If it is in other words, a decimal, it's got to be a negative number. If there is a whole number involved, then that's going to be a positive number. The characteristic is going to be a positive number. All right, let's take the log of 0.00523. First of all, I know it's going to be negative. Why? Because I'm taking the log of a decimal. And I can anticipate what my characteristic is going to be. I have 2 spots here, 2 zeros here, before I hit any numbers. Therefore, it's going to be a -2. Let's see if I'm right. Log of 0.00523. Yeah, -2.28149. -2 because I have 2 zeros there before my number starts. Here, I was a -1 because I had a negative, I had 1 0 before my decimal started. If I had a 0 in front there, my number started right after the decimal immediately. So the characteristic can tell me a lot of things, or I can anticipate what the characteristic is going to be. All right, so let's find f if the log x equals 3.8774. Well, I can write this in exponential form. My base is 10. My power is 3.8774, and it equals x. Now, the cool part is that usually, sorry about all the fingerprints, usually you'll have, let's see on mine if I have it. Doesn't look like I have it, but on some calculators, it will actually, instead of x to a power like xy, it will say 10 to the y. In my case, I don't have 10 to the y, so I'm going to say 10 to the power of 3.8774. Did I do that right? Kind of looks right, but I'm going to do it again. Sometimes my fingers don't push the right thing. So I'm going to say 10 to the power of 3.8774. There we go, 7,540. Right? So that's going to equal, if you have the 10x key, go ahead and use it. Otherwise, I'm going to round it, right? Round it. So 7,540 is going to be our answer here. Now, I do know with the characteristic, that's the characteristic right there, I'm going to have a number with at least 3 zeros in it. So I know with a 3, 10 cubed is 10,000, right? Or no, is 1,000. So I know this is going to have at least 1,000 as an answer. Right? So 7,540. It was going to be in the 1,000 range. If that characteristic was a 4, it's going to be in the 10,000 range. If that characteristic was a 5, 100,000 range. So you can kind of get a feel as to what your answer should be by looking at the characteristic. And if that mantissa, like an 8, that's really close to bumping that up to a 4, so that was going to be a pretty big number that I came up with. Okay, one more vocab word that I'm going to talk about. This 7540 is also called the anti-algorithm of 3.8774, the anti-algorithm, or the antilog. And sometimes you even have an antilog button on your calculator. All right, let's try another example. Find x if the log x equals negative 2.41879. Number 1, I know the characteristic is a negative 2, therefore my answer is going to be decimal. And it's going to be decimal by 2 positions, right? So I've got that in my head, so if I use my calculator, I can kind of judge, did I punch in the right answer, or the right keys. All right, 10 to the negative 2.4179, and I've got to change the sign of that. All right, so my answer is 0.00. Remember, 2 zeros because my characteristic was a negative 2, 382. So approximately 0.00382. Get a sense of what your answer should look like by your characteristic. And your mantissa will give you some help too, right? A 4 is kind of right in the dead middle, so my number isn't going to be too large here. It's not going to be an 8. It's not going to be a 9, because that would make it really close to the next number. So let's talk about earthquakes. We saw this example in another video, but not this particular example, but using this formula we saw in probably the previous lecture. So a lot of us live in California, so let's take earthquakes. In 1906, there was an earthquake in San Francisco, and it's estimated to have been an 8.3 on the Richter scale. A lot of damage happened to the city, not only from the earthquake, but from the fire that actually took place right after the earthquake. Water mains were broken, and so there was no water pressure to put out the fires, and a lot of the damage was caused not only from the earthquake, but the fire. In 1971, there was an earthquake in San Fernando in Southern California, and it measured 6.6 on the Richter scale. So we want to know how much bigger the San Fernando earthquake was than or how much bigger the San Francisco earthquake was in comparison to the San Fernando earthquake. So what we need to figure out is, using the magnitude, let's find the shock waves. All right, so using magnitude, m equals log of t, where t is the shock wave. On the San Francisco earthquake, it's 8.3 as the magnitude, so we can rewrite this as 10 to the 8.3 as the shock wave. Now, if we use our calculator and put 10 to the 8.3, we get approximately 19952.6, I can't even read my writing. 1995262.31.5. There we go. Which, in essence, if we round up here, it's 2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 2 times 10 to the 8th. We're going to do the same thing for the 1971 earthquake. Magnitude was 6.6 equals log t. Therefore, we can write it exponentially as 10 to the 6.6 equals t. 10 to the 6.6 on a calculator is approximately 3981071.7, which, if we do this guy, it's about 3.98 times 10 to the 6th in scientific notation. Okay? How much stronger is that? Well, let's divide the two. 2.0 times 10 to the 8th divided by 3.98 times 10 to the 6th is about 50 times larger. Now, That's bigger. We're talking kind of on the Richter scale how much bigger it is. By no means does that mean it is stronger. Well, yes, an 8.3 is stronger. But how much stronger? There's another equation for that. And the 1906 earthquake actually released about 350 times the energy as so the 8.3 released 354 times the amount of energy as the 6.6 earthquake. So there's two measurements about earthquakes. It's the Richter scale, how much larger, and then the energy that the earthquake releases. So if you're interested in this, I would go check out the usgs.gov site. That's the United States Geographical Society, I think is what the USGS, I always call it USGS.gov site. Really kind of cool. They even have a calculator that you can compare earthquakes. So not only in geology do logs occur, like in measuring earthquakes, but in chemistry as well. The pH of a solution is the measure of the acidity in the solution. So definition of the pH involves common logarithms. pH will equal negative log of H plus, where H plus is the concentration of the hydrogen ion, and it's measured in moles per liter. So pH is generally between 0 and 14. In other words, pure water is a neutral solution. It's right in the middle at 7. Vinegar, which is more of an acidic solution, is at about 3, right? The lower the number, the more acid. So here's a typical measuring scale. 7 is neutral. As it gets higher, it's called increasing alkaline, meaning it's less acidity. Versus if you have a lower number, it increases the acidity. Let's work with an example. In normal rainwater has the pH of 5.6. What is the concentration of hydrogen ion in normal rainwater? Well, if the pH equals the negative log of the number of hydrogen molecule, or the hydrogen ion, then we know the pH is 5.6 is negative log of the number of hydrogen ions. We can rewrite this, but I think I'm going to first be kind of clever about this, and I'm going to multiply by -1 to both sides. That way it's not negative log whatever. So I get negative 5.6 will equal log of however much hydrogen ion we have. Now I can rewrite this. The base is 10. The power is negative 5.6. That's going to equal our answer, the amount of hydrogen. All right, so let's get out our phone calculator. All right. 10 to the power of 5.6, and I have to change it afterwards. There we go. So our answer is going to be number 0.0001234, right? 1, 2, 3, 4, 5, and it should be, because it's -5, 25118. And just because it's chemistry, I do know they write things in scientific notation, so that's going to be 2.51 times 10 to the negative 1, 2, 3, 4, 5, 6 moles per liter. Okay. So 2.51 times 10 to the negative 6 moles per liter. Moles per liter. All right, so let's try another example here. The concentration of hydrogen ion in a sample of acid rain is known to kill fish is 3.2 times 10 to the negative 5 moles per liter. Let's find the pH. All right, so we are looking for the pH. Here's our equation. All right, so our pH will equal negative log of 3.2 times 5 to the negative 5. Oh, sorry, 10 to the negative 5. I don't know what I was thinking there. 10 to the negative 5. Okay, and that's going to be a pH equals negative log of 0.000, let's see, 1, 2, 3, 4, 5, 2. So I can stick that in my handy-dandy calculator here. I do know I'm going to get a negative number times a negative number, so that's going to be a positive number in the end. Scientific, no, little calculator. So I want the log of 0.00032. All right, negative, and I'm just going to take the first two digits, negative 4.9. So a negative 4.49 equals the pH. And a negative times a negative is a positive, so the pH of, in essence, acid rain is 4.49. Remember on the scale, normal rainwater was about a 7, so this is very acidy, right? A 4.49 is definitely more acid than a neutral, regular water. All right, that's enough about common logarithms. Let's talk about natural logarithms. Natural logarithms is a logarithm with the base of e, and we denote it as log base e of x will be the ln of x. Logarithm natural, if you want to think of it like that, the ln of x. All the properties of the logarithm still hold hold true because e is a real number. It's between 2 and 3. It's 2.7 something, so that's a real number. So all of the properties still hold true. All right, let's simplify some workings with e. E to the 0, well, that's a real number to the 0th power, so it's going to be 1. E to the first power, well, that's e. The ln of e, that's going to be 0, or the ln of e equals 1, because if we rewrote this, remember the base is e. E to the 1 equals e. Ln of 1, well, it's 0 because e to the 0 equals 1. If we wrote it exponentially. The ln of e cubed is 3 because we can bring the power out front, and I have 3 times the ln of e. The ln of e is 1, so 3 times 1 is 3. The ln of e to the negative 4 is negative 4. Well, because we can bring the power out front, so it's negative 4 times the ln of e. The ln of e is 1, therefore negative 4 times 1 is negative 4. The ln of e to the t, well, it equals t. Same rule as before. We're going to bring the t out front, so it's t times the ln of e. The ln of e is 1, so t times 1 is t. All right, so let's use the property of algorithms to expand the ln of a e to the 5t. So the ln of a e to the 5t. First thing is, I have multiplication going on here. So that's going to be the ln of a plus the ln of e to the 5t. Well, I have a power on the e, so I can bring that out front. The ln of a plus 5t ln e. If you remember, the ln of e is 1, so that's going to be the ln of a plus 5t times 1. In other words, I can expand the ln of a times e to the 5t, as in the ln of a plus 5t. Let's try another problem to expand. The ln of 1/2 e to the negative kt. So let's try the ln, and since this is multiplication, I can write it as the ln of 1/2 plus the ln of e to the negative kt power. Using my property regarding powers, I can bring that out front. So now I have the ln of 1/2 plus negative kt, the ln of e. I'm just going to simplify that just a wee bit. The ln of 1/2 minus kt, and the ln of e is 1, and 1 times kt is still kt. But I'm not done yet because I have division here. So I have the ln of 1 minus the ln of 2 minus kt. I'm almost done. The ln of 1 is 0. So I have 0, oops, that was a weird looking 0, minus the ln of 2 minus kt, and all of that is negative ln of 2, which is a number, minus kt, but I'm going to leave it like that. Alright, so let's use some information to try and solve for a more complicated problem. Let's say the ln of 2 is 0.6931, and the ln of 3 is 1.0986. And we want to find the ln of 6. Well, the ln of 6 can be written as the ln of 2 times 3. And the ln of 2 times 3 can be written as the ln of 2 plus the ln of 3. Now, I'm not using a calculator. I'm using what I'm given in the properties of logarithms to be able to do this without a calculator. Okay, the ln of 2 I'm given as 0.6931. The ln of 3 I'm given as 1.0986. I'm going to add those two together, 0.6931, 7, 11, 18, 19, 7.1. So the ln of 6 is 1.7917, if I did my math correctly. All right, let's try another problem. The ln of 0.5. Now, it may not look that the information we've been given is very helpful, but I can rewrite the ln of 0.5 as in the ln of 1/2. And the ln of 1/2 I can rewrite as the ln of 1 minus the ln of 2. The ln of 1 is one of our nice properties where it's a 0 minus whatever ln of 2 is, and we're given 0.6931, and therefore the ln of 0.5 is negative 0.6931. Not so bad. All right, let's try the ln of 8. The ln of 8 can be rewritten as 2 cubed. And using our property, that could be rewritten as 3 times the ln of 2. Since our ln of 2 we were given as 3 times 0. I'm going to have to look. Just want to make sure. Got popping up things on my computer and everything. Okay. 0.6931. Right? And now 0.6931 times 3 would be 3, 9, 27, carry the 2, 18 is 20. Therefore, 0.0793 will be the ln of 8. So not bad. If I'm given just a little bit of information, I can do this without a calculator. So that's it for this video. Until next time, be seeing you.